All right, let's talk about memory. Memory is, obviously a key part of a computing system. We use memory for two things. We use it to store instructions that tell the computer what to do, but we also use it to store the things that are manipulated, the data, the numbers, the letters, the pictures, whatever it is that we're reading, modifying, and rewriting, right? We think of that as data. And so memory is used for both of those things. Now, the PIC processor is a little different from, sort of a conventional model. Let's take a look at this block diagram of the PIC processor. The first thing we notice is that there's two memories. There's a memory over here called program memory, and then there's something called data RAM. This is basically where your program, your code goes. This is where the data that's being manipulated goes. And this is not always the case. On some of the earlier systems, program memory and data memory were the same. If you go to an Intel processor, it's the same memory. But on these reduced instruction set machines like the PIC processor, you can speed things up by having a separate program memory and data memory. Why? Well, this goes back to pipelining, which we talked about earlier in the course. We want to be able to fetch one instruction while we're executing another instruction. Well, making a memory that you can read from one location while simultaneously writing another location, that's called a multi-ported memory. That's complex. You can do it, but it takes a lot more hardware. Simpler solution is just have two memories. One that we're only reading to get the instructions from, and another one with its own address bus that we can use to request a read from or a write to. It's also helpful because the program memory is 16 bits wide, whereas the RAM, the data memory, is only 8 bits wide. So that lets us simplify our design further by having separate memories. So that's one thing that's unusual. The other thing that's unusual is that this main memory of the system is built into the chip, right? So we call these things file registers, and there's a lot of file registers on the system. Some of these chips have thousands of file registers available inside the chip itself, and that's a little unusual. Again, sort of older microcomputers might have a handful, maybe a dozen, 2 dozen at the most, registers on the chip, and most of your memory came from what was called main memory. And so the typical picture would be we'd have a CPU and would have some registers like A, B, C, and so on, and then there'd be a memory. And the CPU would get most of its data from memory and store most of its data in memory. But there were a few registers inside, kind of like the working register on the PIC, that you had very fast access to. So the PIC processor is a little bit of an anomaly relative to this model. But let me think about this model in what we talk about here, a CPU with some registers on board. But if you want 16 gigabytes of memory, it's probably not going to be inside the CPU, because a chunk of memory that size, it's a separate physical thing. It's a small board, so that usually goes outside of the CPU. And then of course, on something like a laptop and so on, we also have disk storage. And today disk is often something solid state. It's like a main memory, but traditionally these were spinning drives, floppy disks, things like that, or in my case, washing machine sized behemoths that cost a ridiculous amount of money and looked a little more like this. So use that picture. So CPU has local registers, very fast access. It can store more information in memory, slower access. Memory we can also write to or read from something like a hard drive. And whereas this might have, 30 words of storage, our memory might have, 4 gigabytes. Our disk might be 2 terabytes. And if we want to continue, we can go to cloud storage, and this could be petabytes. So we're not going to put 2 terabytes on our CPU next week. We're probably not going to put gigabytes on our CPU. But, 2 terabytes in a hard drive was unheard of 40 years ago. And having a petabyte of storage on a hard drive might be, a trip to Best Buy in 40 years from now. So this changes over time. But regardless of the numbers, there's this hierarchy. There's this hierarchy between local memory. So let me say local reg. And then main memory. And then disk. And I'm not going to bother putting a whole lot of time into the cloud, but the cloud's up there too. We still don't know the best ways to use that, but it's out there. Alright, so here's a simplified view of our memory hierarchy. Again, this doesn't really apply to the PIC. On the PIC, everything is local. We've got 256 file registers sitting inside the PIC processor's CPU, and we don't have any of this business. But on something like a Raspberry Pi, for example, or an Intel processor, right? We have this kind of hierarchy. So this works well in theory. We write our code, and if we have something that we're using for an accumulator, we'll copy it into a local register, and we'll just keep incrementing it and checking it. And if we want to read a variable that somebody defined in our C program, we just pull it out of main memory. Maybe variable x is stored at location 48, so we read location 48. That gives us the value of x. We do our thing with it, and so on. The problem is that anytime we try to access main memory, we get a big performance hit. And this is a feature of how fast CPUs are now. So Grace Hopper used to give talks at the Naval Academy on computer science, and she would take these 12-inch pieces of wire and hand them out to the class and say, this is a nanosecond. And so 12 inches, this is 11 inches. That's how fast we can send a signal in 1 nanosecond. That's how far we can send a signal in 1 nanosecond. About the length of a piece of paper. Alright, well 1 nanosecond, if something takes a nanosecond, you can do that 1 billion times per second. That's a gigahertz. So if we have a 4 gigahertz CPU, that's 1/4 of a nanosecond. That's 250 picoseconds. Well, how far can a piece of information move in 1/4 of a nanosecond? Maybe about that far. So about 3 inches. Well, if you've looked at a DRAM lately, the physical memory card that you put into your computer to make it run faster, these DRAM cards might be this long. Right? Which means that in the time it takes for 1 clock tick of your CPU, we can't even get a signal from one side of that physical memory card to the other. So imagine your motherboard, let's say it's this size, and here's our CPU, and here's our DRAM. And we want to read something from our main memory. Well, at the very least, we need to send a signal over to this board, and maybe the actual, piece of circuitry that's storing our information is over here. We've got to get over there, get that piece of information. It has to travel back. It has to travel back into our CPU. Just from the travel time alone, it's going to take more than 1/4 of a nanosecond. So when you have a 4 gigahertz CPU and you think you can do 4 billion things a second, well, that's an ideal. That's assuming, for example, that you don't have to leave the CPU. But if you only got a few dozen local registers in here and your 16 gigabytes of memory is stored off here, anytime you need to access that, you lose clock speed. You have to wait for this memory access, and what happens when you have to wait? Pipeline stall. What happens with a pipeline stall? Your effective instruction rate bottoms out. And we go from thinking we have a 4 gigahertz CPU to having maybe a 4 megahertz CPU. Because it can take thousands of clock cycles to go off the chip, because it's not just travel time. We have to locate, one piece of information out of 16 billion, and that takes time. You've got to decode your address, figure out where that information is stored. Plus, we have very low low power signals inside the CPU. Not enough power to drive a voltage on these big conducting traces on your motherboard. So we have to pump up the current to be able to drive a signal across your motherboard to your RAM, and that takes time. So all these things kill our performance. So our current big performance killer of interest is going off chip, right? Don't want to go off chip. We want to do everything inside the CPU. But the challenge there is that, the CPU only has, a little bit of local storage. So how do we deal with that? Well, we put something in between our local registers and the main memory, and this is called a cache. And a cache is part of the CPU. It's sitting on the chip, and it's basically a local copy of some of your main. So when our CPU requests a read from main memory, it first checks our local memory cache and says, do I have a copy of location 48? Right, if it's trying to read 48. And if it doesn't, there's nothing you can do. It's got to go out to main memory. It's going to take time. Your pipeline's going to stall and get flushed and so on and so forth. And then eventually, main memory sends you the contents of location 48. So here's what you do. You save that in your cache. Because the way that people write programs, we tend to have what's called locality. Meaning that if I tried to access location 48 in main memory just now, I'm probably going to try to do it again. So this is called temporal locality. Temporal locality says you're probably going to try to access the same location multiple times. And it makes sense. If you look at a typical C program with a loop, you're going to do some calculation and then add it to a running sum. And so you're going to repeatedly read the value of this variable sum, update it, and write it back in to memory. So the first time you try to access it, you have to go out to main memory. It takes a long time, but now you store a local copy in this cache. The next time I say, hey, give me the contents of this memory location, the memory manager looks and says, oh, I've got a local copy of that. And inside, the CPU, this cache memory can send you that value very quickly, and you avoid that pipeline stall. Alright, so that's the basic idea of a cache. And it's essential to being able to keep CPUs running at what a typical modern clock speed is. You've got to have a good cache memory system. So if we think of a library, right? Suppose that you're in a library. I know we don't do this much anymore. We just go online. But suppose you're in a library and you need to look something up in a reference book. So you go into the stacks and you walk back to the stairs and you go up to the 3rd floor and you go to the back of the room and you walk down the shelf and you find where the reference book is, and you take it off the shelf and you look at the table of contents and you find the section that has the information you want, and you flip to that and you find the thing you're looking for, right? Okay, great. What do? Do you put it back on the shelf and go back to your desk downstairs? Probably not, because a minute later you're going to need some other piece of information, and if you put the book back on the shelf, you're going to have to do all of that again. You're going to have to walk all the way back to the 3rd floor and go get that book, and so on. So what do? The first time that you do that and you've got the book, you look up your information, you bring it with you back to your table and you put it down next to you. And the next time you need to look something up in that part of the book's right there, right? That's all that a cache is. It's keeping a copy nearby so you don't have to go back to main memory. Now, of course, in a CPU, you don't actually physically remove the memory, you make a copy of it, but, same idea. Alright, so that takes advantage of temporal locality. There's also a thing called spatial locality. And spatial locality is like, I spent 5 minutes walking over to where this book was on the shelf, and I brought the book back with me, but you know what? There's probably other books in that same area that I'm going to need later on. So instead of just bringing back that one book, I grab a whole bunch of books near it and I bring them all back to my table. You don't want to do this in the library because you're actually removing the book. But now next to me on my desk, I've got not only that book that I just used, but I got 5 or 6 books that were near it. And now I come to a point where I need some other piece of information. It's not in that book that I originally used, but it was in the book right next to it. Well, I've got that in my cache also. So these are all things that are used inside a modern memory management system. So when you access something in main memory, we check the cache first. If we don't find it in there, we get what's called a cache miss. And it usually causes a pipeline stall while we go out to main memory and we fetch what it is that we're looking for. We save it in the cache, but we don't just fetch that one location. We usually fetch a number of locations around it. So we have a page of information. So even though we wanted to access location 48, maybe we grabbed everything from location 32 to 64. And why do we do that? Again, the way we write programs, if we have a bunch of variables, they're probably close to each other in main memory. And so if I wanted this variable x that was stored at location 48, there's a good chance that at location 50 is another variable. And maybe location 46 has another variable. So I fetched a whole page of locations into my cache, and sure enough, a few instructions later, I try to do something with y, and y is at location 50. Hey, I already fetched it. I can just get it out of my cache. Now what's the CPU doing when this happens? Let's say I say something like, increment memory location 48. So there's a state machine, and it basically says, put a 48 on the memory address bus, send a read request, wait till we've got a signal saying, okay, I've got your instruction. Go ahead and send that to the arithmetic unit, set the function code to increment, take the output of that, put it back on the data bus, put a 48 on the address bus, hit the write signal. Right? It's just a sequence of, several steps that have to happen. But when we get to the process of trying to read location 48, it's not in our cache, right? We've got this pipeline stall. And so the CPU basically freezes. It doesn't have to flush the pipeline, but it has to kind of pause what's happening. And then eventually the memory management unit says, okay, location 48 is available now. And so at that point it can read that value, do its thing, and so on. All right, so this gets more interesting when we think about writing into memory. So let's say we read location 48 from main memory. It goes into our cache. We say increment. So now we take the contents that we wrote here and we add 1 to it. Well, unless we write this back into main memory, our main memory is out of sync. And we can't just keep all of our memory inside cache, because cache is small. Main memory might be gigabytes, cache might be kilobytes or megabytes. So when we update something in cache, we need to make sure that main memory also gets updated. And there's 2 ways to do this, 2 policies for doing writes. There's write through, and there's write back. Write through says when I update a location in my cache, it also gets updated in main memory. Well, that's pretty simple to implement, but it's not so great performance-wise. Because if you also look at the way programs are written, we typically update a location many, many times. For example, if I have a loop where I'm adding something to a running sum, I'm going to rewrite the value of that sum over and over and over again. I'm going to add something, it's got a value of 17. I'm going to write that, but then a few instructions later I'm going to change the value to 23. And if I'm spending time going into main memory, paying that big performance penalty, that's needless waste of time. So a write back strategy keeps your updated contents in the cache and lets it be out of sync with the main memory. And you can do that as long as you remember to eventually update main memory. So, main memory might be gigabytes. Cache, a big cache might be megabytes. We can't store the entire main memory in the cache. If we could, we wouldn't need a cache, we'd just put the main memory on the chip. So eventually, if we keep fetching more and more things, this cache becomes full. And so when we need to get more space in the cache, we need to get rid of something. But if that's something we're going to get rid of is something that we've modified that's not in sync with main memory, at that point we need to write back to the main memory. So that's what a write back system is. It's faster performance, but it's more complex because you need to keep track of whether or not something's been modified. So we add something like a dirty bit to each page to let us know if there's changes on that page that haven't been saved. And how do we decide what to get rid of in cache? Well, there's different policies for that. One policy is least recently used. So we keep track of the last time that we read something from our cache, and the one that we haven't used for the longest time, that's the one we throw out. Or we can do least frequently used. Keep track of how often we access a location. Maybe this one hasn't been accessed for a long time, but it keeps getting accessed periodically. So it's more frequently used than something that was fetched recently but not used very often. And this is all, the science/art of people who design these kinds of systems, memory management systems, deep pipelined processors, and so on. Incredibly complex, a lot of options and possibilities. Pretty fun area to play around with. And this is what makes, one processor different from another. One of the things is how it manages all of this memory. All right, the other thing to mention on caches is, our cache is megabytes, our main memory is gigabytes, so there's a limit to this. But we can actually do something a little better in this hierarchy, so we can have our local registers. And we can have a cache, but we can call that an L1 cache. We can add a second cache, which we call an L2 cache. Have our main memory. So when I try to access something inside my CPU, first I look in the L1 cache. And this is small and very fast. And if I find it, great, I can fetch it from there, no delay at all. If I miss my L1 cache, I can go and I can look in my L2 cache. And this is larger, but maybe not quite as fast. And so it's slower, but still faster than main memory. And so this is basically a cache of my L2 cache, which is a cache of my main memory. So this might be kilobytes, this might be megabytes, this might be gigabytes. So when I have a lot of locality, temporal and spatial, I can just groove on my L1 cache, totally deal with that very fast access, right? And the fastness is partially from the size. If it's only a few kilobytes, decoding is pretty quick. It's a few levels of multiplexer. So very rapid access here, and once in a while I might go outside, that local region and want some other value. But if I've already fetched it from the main memory, it's still going to be sitting in my L2 cache. And so I would grab it from my L2 cache, copy it into L1, and then in the future I can use that. Whereas the value that I might have bumped out from here, instead of going back into main memory, is sitting in my level 2 cache. And so it's still pretty quick to get it. It's quicker than going off chip. In some processors, we also find a level 3 cache. So you can extend this hierarchy in that way also. Alright, well, what about the other side? What about on the other side of main memory? Because our main memory might be gigabytes, but a lot of our programs, you look at a typical video game, it's 80 gigabytes just to download it from Steam. That's not going to fit in our main memory, right? So this is where we start using our disk storage. And there's a way we can actually take our disk and treat it in some sense like an extension of main memory. So we have our physical main memory, but that's a piece of something we call virtual memory. And whereas main memory might be gigabytes, virtual memory is effectively unlimited. It's limited basically by the size of our hard drive, which is terabytes or more. And so how does this work? I mean, so all of these things, you could spend weeks talking about these in a computer architecture course. And if you're CS track and you get to university, you'll potentially dig into computer architecture and take apart these processes. So this is a quick overview, but basically the idea is when you want to access memory location, I'll just keep picking on memory location 48. You want to access a particular memory location. Well, it might be that that's sitting in your DRAM, or it might be that it's actually sitting in something called a page file, which is on a hard drive. And the main memory in some sense becomes a cache on this much larger memory that we're keeping in a big file on our disk. And so at any given time we have a few billion bytes of memory sitting in this dynamic RAM, this DRAM. And if all of our memory needs fit in that size, that's great. But if we're working with maybe an array that's 1 trillion by 1 trillion, a matrix, and so we need a lot more than a gigabyte or a few gigabytes of memory, we take those memory locations and we store them in a file. We put it on our hard drive. And when I try to access a memory location, the memory management unit checks to see if that location is sitting in our DRAM. And if it is, right, if it's not in any of the caches and we go out to main memory, if it's sitting in that DRAM, DRAM delivers it to you and you're good to go. And it took you a few clock cycles of stall. But it may be that this location is not in our DRAM. And so location 48 in our virtual memory is not necessarily location 48 in the DRAM. In fact, it's probably not. It might be stored somewhere in here, or it might not be in our memory at all. It might be sitting in this file. And so we can get what's called a page fault, which means the CPU is asking for something from memory, but it's not in our memory, it's on the page file. And so we need to go out to that file, find where that location is stored, pull that into our memory, so that now location 48 is available. And that's exactly like a cache miss, except the consequences are much more complex because we don't have hardware typically that will open up this page file on disk and find the missing location. This has to be done in software. So think about this. We have our CPU, it's executing instructions, it's just about to execute an instruction that says, I don't know, increment file register 48 or memory location 48. But before it can do that, it's got to do a few million instructions to go out to this disk, look for this file, open it up, find a particular location in it, read the value, pull it into main memory, and so on. So this creates an exception, which is a software version of an interrupt. And when this interrupt occurs, basically everything is paused. This thing that you were trying to do to location 48 goes on hold, and we start this whole sub-process of resolving this page fault. And you know, think about what it takes to open a file on disk and pull in its contents and so on. It's a lot of work. So a few million instructions later, this location we were trying to open is now sitting inside our dynamic memory, our main memory, and the instruction is reset. And we go back to the beginning and we say, hey, let's go ahead and access location 48. And this time the memory management unit says, okay, yeah, I've got that for you. It's in your DRAM. And then that gets loaded into your caches. And then the next time that you try to do something with that, it's sitting hopefully in a local cache, and all of this gets avoided. So when we add virtual memory, we have the benefit of thinking that we have, you know, this much larger address space. And so, you know, our machines, our CPUs are typically 64 bits. Well, how big is 64 bits? Right? How many different locations can we access with 64 bits? Well, that's 16 billion, roughly. Or 16 million trillion, so 16 million terabytes worth of information. And you know, it's going to be a while before we have a DRAM chip that can store anything close to that. But it's irrelevant to our programs. Our programs can think that we have, you know, much more memory than what's actually available. And we kind of get that for free from a software perspective. We can just say, you know, here's the amount of memory I want, and if it doesn't all fit in DRAM, the memory management system and the operating system arranges for this virtual memory set up, and we can pretend we have a lot more memory than we actually do. So there's overhead to all of this, of course. Mostly overhead in terms of complexity, cost, power consumption, physical size, and so on. So we don't see these things in like a PIC chip, which is designed to be a reduced instruction set, very inexpensive, very small, low power, and so on. But on something like, you know, an Intel processor sitting inside your laptop, you've got this virtual memory system, and your programs think that, you know, you've got a lot of memory. And this is why, you know, you can have 4 gig of main memory, you can have 32 gig of main memory, and you don't have to recompile your code or, you know, run a different program because there's a memory management subsystem that works in conjunction with the operating system to manage this transparently to the CPU. So that's a little bit about virtual memory. And then, yeah, there's cloud storage, and we're not really ready to talk about how the cloud fits into all of this. Most of us use the cloud as infrequently accessed offline storage, mostly for files, right? We don't really tie it into our memory systems, but you know, if you run a large database system, it's kind of the same concept, right? This stuff that's in the cloud is an extension of your local disk system, and so this is interesting to see where this goes in the future. All right, so that's a little bit about memory. Again, if you're CS track, we'll get into more of this in some of the other courses, and at university, you'll get into a lot of other details. But from a microprocessor perspective, it's this hierarchy of storage that's probably most interesting to us. All right, thanks.